Well friends, in the earlier module we have discussed about the propagation of electromagnetic waves through different types of media, conducting as well as non-conducting. We also discussed about the reflection and refraction of such electromagnetic waves from the interface of two media. Now, as a part of communication electronics, we have to think about transmission of electronic signals from one place to the other. Especially when we want to transmit the signal through a closed system, we have to think about what is known as transmission lines. So, in this module we will discuss what are the different types of transmission lines, what are the mathematical and computational aspects, how to derive the results related with transmission lines, etc. So, step by step we will go on discussing some of these points at an introductory level. After going through the contents of this module, you will be able to know about different types of transmission lines and their characteristic features. We will try to understand the lumped and distributed models of transmission lines. Also, we will understand the mathematical treatment of two-wire transmission line equations and the terms like characteristic impedance and propagation constant. We will also know about the numerical and computational aspects associated with transmission lines. Transmission lines can be described as a system of conductors generally used for transmitting electrical signal from source to the load. For a beginner willing to study basics of signal transmission, transmission line may be viewed as an impedance matching circuit designed to deliver power from the transmitter to the antenna and maximum signal from the antenna to the receiver. The electrical signal to be transmitted may be analog or digital. In general, the type of transmission medium, the length of the transmission medium, the bandwidth and the bit rate of transmission of the signal are the important factors to be accounted for while discussing different types of transmission lines. In the case of digital transmission, the maximum bit rate that can be used for transmission depends upon the bandwidth associated with the transmission line. Bandwidth for different materials is different for different transmission media. Hence, the transmission media is one of the important parameters associated with such transmission lines. Depending upon the nature and type of transmission, several types of transmission lines, which are also referred as transmission media, having different geometries, can be found to be described in literature. Some of the transmission media are two-wire transmission line, coaxial cable, twisted pair lines, optical fiber, microstrip lines, parallel strip lines, etc. Generally, we deal with transmission lines with moderately low power. However, we can have power transmission lines having single conductor up to 2 lakhs of volts, as well as multi-conductor transmission lines more than 2 lakhs of volts made up of aluminum. Can we have a single type of transmission line for all types of applications? The answer is obviously no. Every type of transmission line has its own merits, demerits and limitations of some kind due to various reasons. One has to select a proper type of transmission line for the desired operation. One has to take into consideration the characteristics like bandwidth, power loss, physical size, etc. For example, coaxial cable has high bandwidth, no dispersion, but the physical size is large. Strip lines, on the other hand, have high bandwidth, are small in size, but have low power capacity. The capacity and the skin effect affect the speed of transmission of twisted pair lines. We can have several such examples. Coaxial cable, in which the space between the inner and the outer conductor is filled with some insulating material, is a better choice than the twisted pair line, since it reduces the adverse effects arising due to skin effect and enhances the capacitance. The transmission range is also remarkably large, which are several hundreds of meters with 10 megabits per second as the transmission rate. Two-wire open lines consist of a pair of open wires insulated from each other and are generally useful for transmission over a distance of few tens of meters with moderate bit rate of less than 20 kilobytes per second. Modem is an example using this type of transmission line. A crosstalk problem can arise in the case of this type of transmission line. Electrical noise, which varies randomly, is one of the prominent factors causing distortion, attenuation, and thus hampering the quality of the signal transmission along the line. Ideally, we expect total transmission of the signal without any loss of power at a very high speed through the transmission line. However, with practical transmission lines, it is not the case. There is always some reflected signal and power loss along the transmission line. Frequency of the signal also matters significantly in theoretical aspects of transmission lines. How to account for all such things? What one should do to avoid or minimize such undesired happenings? For getting answers to such questions, it becomes quite but essential to study the theoretical aspects of transmission lines. Let us go through some of the important mathematical aspects associated with transmission lines. Consider a two-wire transmission line with generator, which is the source of signal to be transmitted at one of its ends, and the load at its other end, known as receiving end. Let Zg and Zl denote impedance of the generator and the load respectively. It be remembered that in normal AC signal transmission, the voltage and currents are assumed to be in phase with each other throughout the circuit. When and to what extent such assumption is valid? We know that an electrical signal is characterized by amplitude, phase, frequency and shape. How these factors are affected when the signal travels along the transmission lines? These and many other points need to be attended for in the study of transmission lines. When a time-varying electrical signal is passing through the transmission line, we have to account mainly for four types of electrical quantities called as transmission line parameters, which are the characteristic features of the transmitting media. Namely, we have to account for the series resistance per unit length, series inductance per unit length, shunt capacitance per unit length, and shunt conductance per unit length. These are symbolically represented as R, L, C and G. These four quantities are known as transmission line parameters. The parameter R and G correspond to the resistivity of the conducting medium of the transmission line and the dielectric separating the two conducting wires in the transmission lines respectively, and decide about the dissipation of energy along the transmission line. The parameters L and C correspond to the speed of transmission of the signal, that is magnetic and electrical energy, in accordance with the phase difference between voltage and current along the line. A small section of the transmission line can be described using all these four parameters as shown. The series resistance depends upon the factors like temperature, spiraling of stranded conductors, bundle conductors arrangements, etc. The presence of magnetic and electric fields around the conductors is the main cause giving rise to the series inductance and shunt capacitance. These parameters depend upon the geometry of the transmission line. Generally, the transmission lines are insulated and have air as the surrounding medium. The shunt conductance accounts for the leakage current flowing across insulator and air. The leakage current being small compared to line current is generally neglected and not taken into consideration in the transmission line modeling. The breakdown strength of the dielectric medium limits the voltage of the transmitted signal, which in turn limits the power carried by the transmission line. It be noted that this property is independent of the frequency of the signal. How much is the breakdown strength? For air, the breakdown strength is few million volt per meter. In one of the earlier modules, we have discussed about the concept of lumped and distributed components. While analyzing transmission line, we have to take cognizance of this aspect. The frequency of the signal to be transmitted and physical dimensions of the transmission line are the two prominent factors to be accounted for in such analysis. Let us see how. If the frequency of the signal to be transmitted is small and the distance of transmission through the transmission line is small as compared to the wavelength of the signal, then the capacitive and the inductive properties of transmission lines can be neglected and the transmission line parameters can be treated as lumped parameters. However, at microwave frequencies, the wavelength of the signal is very small as compared to distance of transmission through the transmission line. Hence, the inductance and capacitance per unit length of conductors becomes dominant. The inductive and capacitive properties of transmission lines can be supposed to be different over the entire length of the transmission line. Thus, analysis of microwave transmission lines needs to be done only in terms of distributed circuit and not by treating it as lumped circuit. Well friends, as discussed earlier, frequency of the signal is very important in the transmission line. Whenever we want to transmit a signal of very high frequency, then what are the effects which are taking place inside the conductor? One of the important effect is called a skin effect. What is the skin effect? See, when you pass AC through the transmission line, then as the frequency of the signal increases, the distribution of the current density shifts towards the surface of the conductor. It increases towards the surface of the conductor while decreases at the center. And because of this, the effective cross section of the conductor through which the current is passing is decreased, and hence the resistance of the transmission line increases. If the resistance increases, naturally it causes a loss of the power due to resistance. This effect is called as skin effect. With increase in the frequency, skin effect increases and causes more power dissipation. DC has zero frequency. So if you consider passage of DC signal, then obviously there is no skin effect. So skin effect is to be accounted for while considering frequency of the signal. For higher frequencies, the skin effect is more. Especially when you consider the transmission of microwaves, then skin effect must be accounted for. Let us discuss in brief about the parameter inductance per unit length of the transmission line. We know that a current carrying conductor is associated with magnetic field around it. Accordingly, sinusoidally time varying current flowing through the transmission line produces time varying magnetic field, which in turn produces an EMF in the line. This electromotive force produced in the conductor opposes the current through the transmission line. This EMF, that is electromotive force, is equivalently described in terms of a parameter known as inductance. The inductance is estimated as magnetic flux linked per unit current in the line. While determining the inductance of a transmission line, both the magnetic flux inside and outside the conductor is to be taken into consideration. In the case of long transmission lines, inductance is more dominant than the line resistance. The series inductance and shunt capacitance depend upon the geometrical arrangement of the transmission line. we can derive such formulae using laws of electromagnetics. Some of such formulae for simple structures are as shown. So far, we have discussed about types of transmission media, transmission line parameters, and some other elementary aspects related with transmission lines. The main purpose of any transmission line is to have 100% transmission. There should be no reflection from the load. However, to fulfill this requirement, there are some problems. For getting answers to this question, that what are the problems, we must know about the term impedance of transmission line. Let us consider a system of two parallel conducting wires which is commonly used for transmission of energy at microwave frequencies. Analysis of transmission line includes mainly the determination of voltage and current along the transmission line at different distances from the generator at a given time. These quantities, that is V and I, in turn can be used to determine the load impedance Z, which is given by V upon I at a given point on the transmission line. Note that Z depends upon the voltage and current along the transmission line, and hence obviously it varies along the transmission line. Transmission line is characterized by its impedance known as characteristic impedance, generally denoted by Z0, which depends upon the frequency of the signal and the distributed parameters R, L, C and G, which represent the resistance, inductance, capacitance and conductance per unit length of the transmission line. We can derive the expression for Z0 in terms of R, G, L and C and omega, which is as shown. Ideally, if the transmission line is infinite in its length, then the transmitted signal will travel only in one direction, that is from source to the load. On the other hand, for finite length of transmission line, a part of the signal will be reflected back along the line towards the generator. The extent to which the fraction of the incident signal will be reflected back along the transmission line is measured in terms of two physical quantities, namely reflection coefficient τ and transmission coefficient T respectively. The reflection coefficient T is defined as the ratio of transmitted and incident voltages. Similarly, the reflection coefficient R is defined as the ratio of reflected and incident voltages. These two coefficients are also expressed in terms of load impedance ZL and characteristic impedance Z0 as shown. Note that the reflection coefficient is denoted by R as well as τ in the literature. From the above expression, it is clear that the reflection coefficient τL is 0 if ZL is equal to Z0 or infinity. Similarly, T will be equal to 1, that is transmission coefficient will be 1 if ZL equal to Z0 or ZL is infinity. The reflection coefficient and the transmission coefficient are complex quantities. Reflection coefficient τ at a distance L from the load is expressed as τL is equal to magnitude of τL into e raised to j theta. The reflection coefficient τ and the transmission coefficient T are related through the relation as shown, namely T square is equal to ZL upon Z0 into 1 minus τL square. Since for two wire transmission line, infinite load impedance implies T equal to 1, that is no reflection, we will have to select ZL is equal to Z0. When this requirement is fulfilled, the transmission line is described as a matching pair of transmission line. If it is not possible to have ZL is equal to Z0, then also reflection coefficient can be made 1 by using stub matching technique to be described later in separate module. Friends, so far we have discussed about different types of measurements and the corresponding formulae. All these and many other formulae can be derived by using the solutions of transmission line equations. Hence, let us try to understand about the transmission line equations and their solution. A two-wire transmission line is commonly used for power transmission and is easy to understand the related concepts associated with transmission lines. Hence, let us discuss the equations with reference to a two-wire transmission line. Consider a two-wire transmission line extended along the z-axis with generator at one of its end and the load at the other end as shown. Let Zg, Z0 and ZL represent the generator impedance, characteristic impedance and the load impedance respectively. Let Vz and Iz represent the voltage and current at a distance Z from the generator along the line. It be noted that different physical quantities related with transmission line can be equally obtained using Maxwell's equations. However, we will use the circuit theory approach using uniformly distributed parameters. The voltage and current are the circuit parameters. The transmission line equations in terms of these quantities derived on the basis of distributed parameters R, L, C and G can be expressed in a convenient form by treating the voltage and current as complex quantities. A small section of the transmission line can be described using all these four parameters as shown. For deriving the transmission line equations, we will apply Kirchhoff's voltage law to the central closed loop and Kirchhoff's current law to the node B on the transmission line. Let us apply Kirchhoff's voltage law to the central closed loop containing the segment AB of the line. Consider 2 points A and B at distances Z and Z plus delta Z along the line. Let V ZT and V Z plus delta ZT be the voltages at points A and B respectively with respect to the lower conductor. Let IZT and Z plus delta ZT be the currents leaving the nodes A and B respectively along the transmission line. As per Kirchhoff's voltage law, we have VA equal to VAB plus VB, which can be written in terms of the quantities as shown, namely VZT is equal to IZT into R delta Z plus L into delta Z dava I by dava T plus VZT etc. Let us call this as equation number 1. Let I and V be taken to represent IZT and VZT respectively. With this understanding, equation number 1 can be written as shown in equation number 2. Let us apply Kirchhoff's current law to the node B of the line. Summation of the currents at B gives IZT is equal to IG plus IC plus I at Z plus delta ZT. Using the expression for current through the capacitor as a product of capacitance and the time derivative of its voltage, and then using Taylor's expansion for voltage and the expression for current through the capacitor, we can get equation number 3. Again, as before, with I and V to represent IZT and VZT respectively, with the assumption of delta Z to be infinitesimally small, the above equation can be written as shown. Differentiating equation number 2 with respect to Z and equation number 4 with respect to T and combining the result, we obtain the transmission line equation determining the voltage V along the transmission line involving transmission line distributed parameters R, L, C and G as shown. Similarly, differentiating equation number 2 with respect to T and equation number 4 with respect to Z and combining the results, we obtain the transmission line equations determining the current IZT along the transmission line involving transmission line distributed parameters R, L, C and G as shown. Use of concept of phasor in complex algebra can be effectively made to express the transmission line equations 5 and 6 so obtained in a very compact manner. For this, let us express the voltage and current as a real part of complex numbers as shown. Namely, Vz t is equal to a real part of Vz into e raised to j omega t, Iz t is equal to real part of Iz into e raised to j omega t. Here Re means real part of Vz and Iz are complex numbers known as voltage and current phasors. The phasor corresponding to a quantity gives its magnitude and phase. Consider equation number 2 derived earlier. Substitute j omega for dabba by dabba t in equation number 2 and then dividing by e raised to j omega t, we obtain the equation number 2 dash as shown. Now, by noting that Iz t is equal to real part of Iz into e raised to j omega t and Vz t is equal to real part of Vz into e raised to j omega t, we understand the equation as shown. Noting all these things, finally equation 2 dash can be reduced to the equation as shown, namely dV by dz is equal to minus z into I, where z is r plus j omega L. On similar lines, we can transform the remaining 3 equations, namely equation 3, 4 and 5 in phasor form. Thus finally, assuming that the signal travels from generator to source along the transmission line in the z direction, we can derive the frequency domain transmission line equation in phasor form as shown, namely E1, E2, E3 and E4. The substitution made while deriving these relations are as shown, namely Z is equal to R plus j omega L, Y the admittance is equal to G plus j omega C and gamma is equal to root ZY, which is alpha plus j beta. For lossless transmission line, R is equal to G is equal to 0. In this case, voltages and currents needed for determination of various quantities described above can be obtained by solving the transmission line equations, which in phasor form can be expressed as shown. Note that the above equations are obtained using the distributed circuit theory. From the solutions of equations E3 and E4, with little simplification, the characteristic impedance Z0 of the transmission line can be shown to be dependent upon the transmission line parameter and the frequency as shown. At microwave frequencies, assuming that R is very much small as compared with omega L and G is very much small as compared with omega C, the propagation constant gamma can be expressed as shown. Here the attenuation constant alpha and beta and their dependence upon R, L, C and G is also shown. Similarly, the characteristic impedance Z0 can be shown to be dependent upon LC only as per the following relation. The phase velocity is given by Vp is equal to omega upon beta, which is 1 upon under root LC. For a lossless transmission line with air as a dielectric with no ferromagnetic material, at microwave frequency, the phase velocity is given by Vp is equal to 1 upon under root Lc, that is 1 upon under root mu 0 epsilon 0, which comes out to be 3 into 10 raised to 8 meter per second. For solving transmission line problems, one must know how to evaluate the mathematical quantities using complex algebra. Let us revise some basic things before we proceed for computing various quantities in transmission line problems. We are familiar with the representation of a complex number on complex plane. For example, see the representation of a number z is equal to x plus zy, where j is positive square root of -1. A complex number can be expressed in different ways. In Cartesian coordinate system, a complex number z is equal to x plus zy is represented by a point pxy in complex plane as shown. The point P can be equally expressed in terms of the magnitude of z and the phase angle theta using polar coordinate as p r theta, where the magnitude of Z, which is called as mod of Z, generally represented as R, is equal to under root of x square plus y square, and the phase angle theta is defined as inverse tan y upon x or arc tan of y upon x. From simple trigonometrical calculation, we get the result x is equal to r cos theta and y is equal to r sin theta. Thus, we have z is equal to r cos theta plus j into r sin theta. This is known as Cartesian representation of complex number z. Now, using Euler's identity, e raised to j theta is equal to cos theta plus j sin theta, we have exponential representation of z as z is equal to r into e raised to j theta. Symbolically, it is represented as z is equal to r angle theta. Note that the square root of a complex number z is given by z raised to half is equal to under root r, that is z raised to half angle theta by 2. Sinusoidally time varying quantities like electric current and voltage with constant amplitude and frequency can be expressed in phasor form. Such representation becomes highly useful in AC circuit analysis and electromagnetic field theory. According to one of the two main conventions followed while solving electrical circuit problems using phasor notation, V is equal to V0 angle theta is taken to represent the sinusoidal voltage, Vt is equal to V0 sin omega t plus theta, where omega is the angular frequency of the signal. It be noted that phasors are simply complex number having magnitude and phase. One must know about the elementary operations in complex algebra like addition, subtraction, multiplication, division, etc. Have a look at some of such manipulations shown here. The knowledge about two more elementary formulae for multiplication and division of two complex numbers in polar form are highly useful while solving transmission line problems, which are as shown. With this much background, let us see a small problem in transmission lines which needs the use of above mentioned formulae. The problem reads like this: a transmission line comprising of two long parallel conductors is characterized by the following distributed parameters R, L, G and C as shown. Calculate the characteristic impedance Z0 at frequency f is equal to 1.5 gigahertz. Let us make conversion of the given physical quantities in SI units. The conversions are as shown. Observe the substitutions and subsequent manipulations made in finding out the characteristic impedance Z0. The values of R1 and theta1 needed are to be computed as shown. The value of R2 and theta2 needed can be computed on similar lines as shown. Substitution of the values and using appropriate formulae, we get Z0 as shown. Note that we have to maintain the decimals as per the accuracy expressed in the problem. Study of comparative aspects of several options of any job, any activity, any purpose reveals many interesting points related with the system. Similar is the case with transmission lines. Which type of transmission lines are important, DC or AC? Why? Are there any limitations? So many questions may arise in our mind. There are many advantages of DC transmission lines over AC transmission lines. For example, DC lines suffer no skin effect. Due to this, cables used for transmission line can be made thicker to decrease the resistance of the line. DC lines possess slightly more transmitting power per cable as compared to AC lines for similar equivalent conditions. DC lines can carry approximately double the power as the one carried by AC line at the same voltage. For any long lines, System stability of DC lines is better as compared to AC lines. Intermediate switching stations are usually required for long distance AC lines, which further results in increasing cost. DC lines can carry at least twice as much power as an AC line of the same voltage. The applications in which AC lines are costly and are impractical, DC line is a good alternative. Underground or underwater transmission over a distance of 50 km or more is one of such examples. Multi-cable DC transmissions are used to reduce the cost. If DC lines are so much advantage, then why to use AC for transmission of signals? In literature, many aspects such as theoretical, engineering, technological and economical are discussed in connection with AC and DC transmission lines. One should read and enhance the level of our knowledge about them. One should have a habit of comparative study of any two options available as a solution to a given problem. Transmission lines, whether DC or AC, is a good topic in this regards. Well friends, to summarize, we may say that the transmission lines are to be analyzed by treating as distributed system at high frequencies. The performance of the transmission line is highly affected due to the effect which is called as skin effect. Shifting of the current density towards the surface as the frequency is increased is called as a skin effect. Due to skin effect, the loss of the power increases. For DC transmission lines, there is no such skin effect. Reflection coefficient and transmission coefficient are the two physical quantities which decide about the transmission and reflection of the power along the transmission line. These two quantities are complex numbers. Transmission lines can have various power capacities: low voltage transmission line, high voltage transmission lines. Thank you.